Good afternoon. My name is Daniel Cooley, and I'm the Chief Strategy Officer at Silicon Labs. I'm here today to talk to you about Getting Smart, 20 years of MCU technology, including a look back and forward on the key technologies enabling microcontroller market. Before we go too much further, I'd like to share a little bit of background information about myself. I've split my career in three main phases, one in chip design as an engineer, one in product management and overall business leadership, and lastly as the Chief Strategy Officer for the company. We live in Austin, Texas. You can see a photo here of my family, three boys, and this photo was taken just after the third one was born. So before we go too much further into MCU technology in the embedded markets, I thought it would be useful to take a step back and see where we fit in the overall compute ecosystem. And I've divided the market here into four main pieces. One is high performance compute, mostly centered in the data center. The second is in PCs. The third is in mobile compute. And the last one is in embedded. And you can see here that there are very different requirements, constraints, and careabouts in each application. And these things vary by many orders of magnitude, whether it's memory, power, battery life, cost, or connectivity. They're all very different. And when I talk about this with people, I think about it and I discuss it in the analogy of transportation, where high performance compute is the high-speed rail networks that are getting lots of people and goods around. The laptop and PC space is kind of the workhorse. That's where the semi-truck comes in. We see a lot of those on the roads. Mobile is more about individual people and performance. This is like MotoGP. And lastly is embedded. And these are lighter workloads that have to send smaller amounts of data around. And that's more like an e-bike in terms of the overall landscape. And from a bike to a high-speed rail, these things are also orders of magnitude different in what they do. So I always like that analogy. So we're going to focus today on MCUs and embedded applications. And we're going to talk about this in four main technology areas: compute, connectivity, security, and intelligence or smart. And I've selected four timeframes to discuss here because I feel like those were the kind of most intense timeframes when a lot of the seeds were being sown and laid down for how the market was going to develop. And of course, compute, connect, secure, and smart are all happening all simultaneously. These things do not, they very much overlap. But I feel like what happened in 2007 to 2011 enabled the next wave, and connectivity enabled the next wave after that. And really we're generally riding the same trends that were created during those time frames. So let's take a look at each of them. There's a catalyst event, there's what happened before, what happened after, and importantly, we're going to take a look at some products as well in each of these, because I feel like it's important not to discuss trends, but also what was being delivered to the market. So in compute, I settle on 2011 to 2011. And 2007 was an important year because that was the year that ST launched the STM32 product line. And this was a 32-bit Cortex-M based product line that was different than what came before, because most of what came before were proprietary architectures. So every company had its own instruction set, its own tool chain, and the software was not very portable from chip to chip as a result. So ST launched this product, and what happened over time was that the proprietary architectures lost share, and the market solidified on ARM. And you can see that here in the volume that was shipped based on MCUs from 2009 to 2014. That was kind of the big uplift as the market was adopting it. ARM went from 20 million to almost 1 billion units in just 4 years. That's very, very fast adoption in embedded. And that trend is continuing into today. So here you see the 2019 embedded market study delivered by AspenCore, and they asked the question, which of the following 32-bit chip families would you consider for your next embedded project? And you can see that ARM was 8 out of the top 10 MCUs were based on the ARM core. So I think we can all say we are mostly working on ARM cores today, and there's some RISC-V that's coming into the mix, but for the most part, it's still an ARM market. So what kind of products were being delivered? Well, I chose one at the beginning and the end of the era, as well as one from today. And we see the STM32, the Kinetis family, and Ambic's Apollo family here. So you can see the common Cortex-M architecture there, and then the progression in key technology, in clock speeds, in memory, in power efficiency, and in overall peripherals. So everything is getting more advanced. We're seeing better power efficiency, higher clock speeds, more compute. In general, the MCUs today are doing a lot more than the MCUs back in 2007. And a key enabler of that was standardizing on one instruction set and one tool chain, and then a lot of reuse over the years. And that leads us into the next era, which is about connecting all of these MCUs together. This is where we start to see the IoT emerge, and you hear that term start to come up more and more. I picked 2012 to 2016 because I feel like a very important step in this journey was Apple's choice to embed the Bluetooth Low Energy standard, Bluetooth 4.0, into the iPhone. So specifically the iPhone 4S. So before this, in short-range wireless at least, most of the applications were picking up proprietary-based protocols. And this was multi-chip solutions in many cases with a lot of discrete components or a transceiver and an MCU running a simple stack. And the idea of chip interoperability was almost non-existent out in the market. There was very little interop, and that was really holding the market back. It was not going to scale to hundreds of millions or billions of connected things out in the world. And as a result of Bluetooth and many other initiatives here, we see wireless alliances and ecosystems driving standardization and interoperability. And I got to say, Apple didn't drive that. It wasn't just Bluetooth. It was the whole ecosystem realizing that we had to do better than proprietary protocols that could not interoperate between different chipsets. So here's two examples of the trends that are happening. One is the worldwide BLE-enabled shipments in billions of units, separated between cellular and embedded. And you can see the rapid adoption by the smartphone, the mobile devices. By 2014, we saw over 1 billion phones a year shipping with Bluetooth Low Energy. And then we see the adoption on the embedded side. So all the things we were connecting to in green. And now it's about eclipsing. We're starting to see more embedded devices than phones, and that's going to keep growing over the years. The market is saturated on smartphones. It's generally limited by the number of people on the planet, but embedded is not. You might see 10 or 100 embedded devices for every phone that's shipped in the out years. The other chart here is in dollars. We see the embedded wireless TAM. Again, this is mostly short-range protocols. And this is highlighting the difference between standards-based and proprietary. So standards-based including Bluetooth, Wi-Fi, Zigbee, Thread, Z-Wave, and proprietary as well, the proprietary protocols that are out there. And we start to see mass adoption of the standards-based technologies at a higher pace than proprietary. It is important to note that proprietary is not going anywhere. Proprietary will be around for a very long time, and there's very good reasons in all of these markets to do that. But most of the growth in terms of dollars and volume is going to be on standards-based technologies. So what kind of products were we developing? In 2012, I think a great example is Nordic's NRF5281, NRF51. As we were exiting the era, we saw products like TI CC2640, and if we come to today, we see things like the Silicon Labs EFR32 BG22. So we see Cortex-M everywhere. That's still the case. Faster clock speeds, more memory, and more peripherals on these MCUs. And that trend is going to be the same everywhere in all these things. We see advancement of the standard Bluetooth 4.0 to 4.2 to 5.2. We see power efficiency, and in wireless devices, especially battery life is very, very precious. So we see the power efficiency getting orders of magnitude better over the years. And importantly, these MCUs are doing a lot. They're still doing a lot. They're wireless devices, but they're mostly MCUs for applications. So we still have all the peripherals you would expect, all the IOs, and all the security technology that's coming in very rapidly. So that leads us to the next phase, the next era here, which is more about security. And we have spent years talking about security, and we're happy to finally see the security products coming into the market. So we've selected 2017 to 2021, and the real catalyst event being in 2017, ARM's launch of the PSA certification program, and that stands for Platform Security Architecture. This is an attempt to try to standardize what a secure application or a secure product can be and what we need to do in the supply chain to enable that. Before 2017, I'd say that security was certainly immature in the market. There was not a lot of ways to secure your application, and frankly, most developers weren't really sure how to secure their application. And an example of that is we saw a lot of examples of things like unlocked debug ports out there, and so it was very easy to break into these devices. And after this era, you're going to see most MCU providers embedding dedicated security processors and technology into the product. And let's talk about why we're doing that. Well, you see a lot of news articles coming out all the time on hacks, and I wanted to pick three. One is in door locks. You're starting to see a lot of MCU technology embedded in door locks. We don't want to, we want to have locks that lock. Second is in automotive. This is a famous hack where somebody was able to remotely disable a moving automobile from 2015 that I think definitely struck a bell in the industry. And then the last is in health. And so we're starting to see a lot of technology embedded into our body, embedded into health, a lot of data privacy concerns that are starting to come into play there. And these are just three examples of what's going on. There's many, many reasons why you need to secure your embedded application. And we'll talk more about that. So what's happening in the ecosystem? Well, embedded markets are very different than things like payment systems and cell phones in that they're very, very diverse. The supply chain has many companies feeding into many different end applications in many different geographies. And as a result, the governments are starting to step in and legislate to protect consumers in a way that they didn't have to for some of the other applications. An example here is what's going on in the United States. California led the way with a Senate Bill 372, which was an attempt to start securing IoT devices, and many states are now following suit here in the US, and there's even federal regulation that's just being now authorized and adopted. The same is happening throughout the world. So this is just an example. The same is happening in Europe and in other geographies. But governments don't tell us what to do. They tell us how. They don't tell us how to do it. They tell us kind of what to do. We're starting to see organizations like Etsy and NIST stand up and define standards around this that we can then build products that comply with. So this is an example of the EN 303645 and NIST's 8259A that are working their way through. And this is starting to get more specific and more deliberate about what the devices can and can't do and how they need to certify or not. So very excited to see this because I do feel like we need to do the right thing in securing our end devices for safety and for data privacy. So what products are coming out to enable this? So we then picked three MCUs, Freescale's Kinetis, Cypress's PSOC 6, and Silicon Labs EFR32BG1 with Secure Vault technology. So the same story that you saw on the last pages is happening. We see Cortex-M, we see clock speeds improving, more connectivity coming into the mix, more memory, better power efficiency, and still writing down Moore's law. But what we're starting to see now in this era is a lot of advanced security technology coming into the fold. We're seeing secure enclaves, Trust Zone, which is a new from ARM, multi-stage ROM boots and puff key storage and secure identity, glitch protection, DPA countermeasures. This is just technology in MCUs that wasn't available 5 years ago. So the market is realizing that we have to go and do this and starting to rise to that challenge and make the products. And these aren't in mass adoption yet. They will be coming, just like the prior eras. We talk about connectivity ending in 2016, and the market's really growing right now, but the the trend was set back then. The trends are being set now. The trends are being set now in security, and you're going to see devices coming out into the market in the next couple of years that are far beyond what we have available today. It was very exciting. And that leads us into the next era, which is completely in the future, which is making things smart. And this is where this has always been going. You know, from the beginning, it's been about making things do more and smarter. And it started with just adopting MCU technology in general. Many applications 20 years ago or 30 years ago didn't even have an MCU. They were based on discrete systems with fixed function capability. But then we saw software enter these devices through MCUs, and that was, you know, the first big step. The second big step was connecting them to the phones, connecting them to the gateways, connecting them to the internet. And the third one, as we talked about, was driving security. We'll talk about why that's really important in a second. But lastly, where it's all going is making devices more and more smart. And the catalyst hasn't happened yet. I can't point to one thing that's happened and say that was it. And maybe in hindsight, we'll get there. But what's happening today is that there's not a whole lot of processing on these end devices. Most of the data that they're generating has to be sent out to the cloud, and through the networks, you know, they're flooded with what I call garbage data, and that data is mostly noise, very little signal in there, frankly. And that will change in the future. We're going to see computing distribute hierarchically between cloud, gateway, and edge nodes, and the compute will happen where it needs to happen, not in the cloud where it's only capable of happening today. So why are people doing this? Why would they even want to make these devices intelligent? Here's 3 examples in industrial, security, and health applications. One is in an industrial coffee maker. And really this is about reducing downtime and extending lifetime of critical equipment. So this is a real example. We had a customer at Silicon Labs that was coming to us saying they needed to redesign their coffee platform for predictive maintenance. And the reason why is that if they had to go service a coffee maker more than once, so if they had to do it 2 times in its lifetime, they lost money. The ROI was negative and they would go out of business. So they started designing their products to be serviced once and only once. Instead of trying to build it to never break, which is very hard to do, and typically fails catastrophically when it does, and unpredictably, they design them to be serviced and maintained once on a predictable schedule. And so if you do that, you're able to improve your overall business model for these companies, and stores can plan, and everybody wins. The next one is in home security or security in general, and it's about reliability for emergency systems. One of the biggest challenges in security is false alarms, and false alarms are dangerous and expensive. They're dangerous because people stop paying attention. If the alarm's always going off, people just stop. And so they may not get out, or they may not realize they're in danger. And the second one is expensive because you're constantly responding. You're sending police, you're sending emergency services out to respond to these alarms, and they may stop coming, or the costs may go up as they have to do that response. So if you're able to make these systems smarter and realize when they should and should not trigger, then it's safer and cheaper for everybody. The last one is in saving lives. So in health technology, there's a lot of progress being made by adopting machine learning and artificial intelligence. This is just a representative example. What we saw, a biker fall down and become unconscious, and the watch called the police, the emergency services, the ambulance, and came and found the person, and I hope they were safe in the end. But this is kind of where this is going. You're going to have technology it's looking at you and whether you're healthy or not and responding accordingly. But to do that, you have to make it smart. So there's a lot of intelligence coming, but I sometimes have to connect dots. And one of the dots that we're connecting for the market right now is that you can't do all of this intelligence. You can't make these things smart and truly rely on them unless you trust them. You have to trust these end devices inherently. And what I like to say is that edge intelligence cannot scale without trust. And that means these devices, down to the very end nodes themselves, have to embed a lot of security technology. And I classify this in two ways. First, the end devices have to know they're talking to the right cloud, and vice versa. The cloud has to know it's talking to the right end device. And there's a whole lifecycle management here that comes in from commissioning through updates over its lifetime and all the way through decommissioning and returns. And to truly enable a secure lifecycle for a product, it requires from the ground up thinking on security and the technology that goes within. Second thing is that the data on the device has to be protected. So there's multiple reasons for this. Some of it's government regulation that we saw earlier. You know, we don't want private data, PII, to get out into the world. We don't want hackers to be able to find out information about you. But more, you know, commercially, machine learning technology itself is based on proprietary data sets. So companies spend so much money trying to create their algorithms, their inference engines for identification and classification. And this data has to be protected. These companies need to put the inference engines on very, very cheap MCUs that get sold into the market and know that their technology, their IP will be protected on those end devices. And they're not going to be able to do that. They're not going to be able to update those devices and trust that the inference is right unless there's deep security within the application itself. So we cannot have true edge intelligence without security, without connectivity, without standardization on compute. These things build off each other. So the technology that's going into the intelligence, well, there's not products yet. I can't look at any, you know, like the last eras and say, oh, here's the MCUs that are enabling intelligence today. There's new technologies being invented and you know starting to become integrated, but it's not mature. And these technologies are evolving rapidly, which is great. But I think it's nothing like we're going to see in a couple of years' time when most MCUs are getting into finer pitch Moore's law geometries and the inference topologies are stabilizing. So right now it's about inference acceleration, convolutional machines, matrix processors, fast FFTs, and various different kinds of neural networks depending on the compute and inference. So whether it's CNN, RNN, spiking neural network, or you know whatever's coming next, we're starting to see more of these technologies mature to the point where they're coming out of HPC, kind of high performance compute, and starting to be looked at for embedded. Next, we're seeing a lot of startups. So nothing stirs the market like startups, and we have seen a new wave of startups in AI that we haven't seen in a very long time in semiconductors. Not all will make it. Some will make it very, very big, but we're seeing different kinds of startups targeting different kinds of applications with different technologies. This is just a small list here. There's dozens and dozens that are out there, and they're all taking their different approaches. The last is an emerging ecosystem that's enabling machine learning down into the embedded landscape. So we see TensorFlow move into TensorFlow Lite. We see TinyML. We start to see open software libraries that developers can implement down to the MCU, which is really important for very simple applications right now, like a wake word, and will be getting more advanced over time. So that's 20 years of MCU technology. We see standardization on compute, standardization on connectivity, standardization on security, and in the future, standardization on machine learning. And when you tie all these pieces together, you start to see embedded computing going into everything in a more scalable way. I'm very excited about where it's all going. I think that, you know, kind of taking a hat and what's on beyond after this, the idea that there's not a chip put in something in the future will seem foreign. I think chips will be everywhere, and it's going to drive a new wave of innovation actually as systems developers take a look deeper into their supply chain and realize that they could take advantage of technology down to the transistor level in a way that they couldn't in the past. So that's it for this keynote. I really appreciate your time today, and would like to open it up to Q&A now. Thank you.